Hello everyone, welcome to another video on differential calculus, and in this one I'm going to be focusing on rules of differentiation, but I want to start looking at notations of derivatives first. Once we're done with notations, we'll move on to rules and we'll focus on 8 rules of differentiation. All right, so let's look at notations then. Notation number 1 that we need to focus on is Newton's notation of the derivative. Newton's notation of the derivative. So if you are given y is equal to f of x, whatever f of x is, Newton's notation for the first derivative is written as y dot, like this, and that represents the first derivative. Y dot dot represents the second derivative. So in other words, when you're given a function f of x, you differentiate the first time, it will be y dot. If you differentiate the second time, it will be y dot dot, right? That's the second derivative. And then you can carry on, etc. In other words, if you want the third derivative, there will be 3 dots at the top, on the top there, right? That's Newton's notation. Let's move on to the second notation we will need to focus on is Leibniz notation. So Newton's notation, we're done. Leibniz notation of the derivative. Again, if you're given the function y equals f of x, according to Leibniz, the first derivative, it will be dy dx. That will be first derivative. Notice that this one here is written as dy over dx, but we read this as dy dx. So I'm going to write here, read as dy dx. dy dx. That's how we read it. Take note of that for the first derivative. The second derivative, we're going to say d squared y dx squared. This is second derivative. Notice how we read this one. This one is read as d squared y dx squared. That's how we read it. D squared y dx squared. And then you can continue, etc. For the third derivative, it will be d cubed y dx cubed, and so on. That's Leibniz notation. Let's move on to the third notation of the derivative. The third notation of the derivative is going to be the famous Lagrange number 3. Lagrange is notation of the derivative. Yet again, if you're given a function y is equal to f of x, for according to Lagrange, the first derivative, it's going to be f prime of x. You remember this from first principles. So that will be first derivative. And then for the second derivative, it's going to be f prime prime of x. This will be second derivative. Notice how I'm reading this one here. It's f prime prime of x, f double prime of x, whatever is okay for you. All right, let's look at, and so of course, etc. You can continue. F triple prime of x, that will be the third derivative, and so on. Right, number 4, that I want us to look at is what we call the differential operator, capital D. The differential operator as a symbol of differentiation, capital D. That's your differential operator. So first derivative, it will be written as this, as follows. D sub x, there's a 1 here, power 1, we don't write. This is first derivative with respect to x. First derivative with respect to x. For the second derivative, it will be dx the power 2, like so. This is second derivative with respect to x. Second derivative with respect to x. So these are the four notations of the derivative that you need to get used to. These are the four notations. Now I'm moving straight to rules of differentiation. Now that we're done with the notations, let me just remind you, notations of the derivative. We have the first notation, Newton's notation. If you're given a function y equals f of x, y dot will be first derivative, y dot dot will be the second derivative, and so on. Leibniz notation, y equals f of x, it will first derivative, it will be dy dx, second derivative d squared y dx squared. Right. Please note that this is notation. You cannot cancel the d's. It's notation. Right. Number 3, Lagrange notation from first principles. You will remember this. F prime of x, first derivative, f prime prime of x, second derivative, and so on. The differential operator, capital D, with respect to x here, there's a power of 1 there, which we don't write on the top there. But if it's bigger than 1, obviously, we're differentiating the second time, you must have the 2 there, showing you that this is a second derivative with respect to x. Right. Now let's move on to rules of differentiation. I'll need a fresh page for that. Rules of differentiation. Rules now of differentiation. Number 1, the derivative of a constant is 0. How do we prove this? Let's look at the proof then. Let f of x be equal to k. Remember, what we mean by a constant is a constant function. That means if this is your x-axis and that's your y-axis, you could have something like this. That would be y equals k. That would be your constant function. And remember, from your knowledge of analytical geometry, the gradient of a horizontal line must be 0. So that confirms it. But let's prove by using first principles here. Remember, that is supposed to be perpendicular to the y-axis or parallel to the x-axis. Right. So we're going to say, therefore, f of x plus h will still be equal to k. Think about this. If this is my x here, what is f of x? It will be k. I increase this by h to some place there where the x value now is x plus h. What will be the value of f of x plus h? It will still be k. That's what we're saying here. So therefore, from f prime of x, this will be equal to limit as h approaches 0 of f of x plus h minus f of x all over h. Substituting, we have limit as h approaches 0 of k minus k all over h. This will be limit as h approaches 0 of k minus k over h. This will be limit as h approaches 0 of 0 over h. This will be limit as h approaches 0 of 0, and the answer is 0. So that ends the proof. The derivative of a constant is 0. So that means, let me just write here, e.g., if I'm told that y is equal to 7, by using Leibniz notation, dy dx must be equal to 0. 7k minus 8, whatever constant it is, dy dx must be 0. So that's the meaning of this rule number 1 here. The derivative of a constant is 0. Remember, they can ask you to prove this in an exam. Prove that the derivative of a constant is 0, and this is the proof. That's how you lay it out. Right. Rule number 1 done. Let's move on to rule number 2. Rule number 2 says, if you have, let's say, f of x is equal to a constant times g of x, which is a function. This rule says, if that is the case, then f prime of x will just be a constant times g prime of x. How do we prove this? Well, let's look at the proof here. So we are saying f of x equals a constant times g of x. And therefore, f of x plus h will be equal to a constant times g of x plus h. Let's go to the formula. F prime of x, this will be equal to limit as h approaches 0 of what? Of f of x plus h minus f of x all over h. Substituting these expressions into that, we have limit as h approaches 0 of k g. I'm using brackets here, but you don't have to. Let me remove this bracket here. I want to remove this bracket here. That one. I want to remove it so that you don't confuse with the bracket I'm about to introduce, which is x plus h. That expression is this expression here. And then minus f of x is that expression. We don't have to put brackets in this case now. K times g of x all over h. Please take note. This expression here is that expression there. And this expression is that expression. Now you can see the common factor is k there. Let me take it out. So limit as h approaches 0 of k, open brackets, g of x plus h minus g of x all over h. Take the k outside. This is going to be k times limit as h approaches 0 of g of x plus h minus g of x all over h. If you notice from the definition, definition of the derivative from first principles, I told you that f prime of x is limit as h approaches 0 of f of x plus h minus f of x over h. That tells you g prime of x, this must be limit as h approaches 0 of g of x plus h minus g of x all over h. So where I see this, I'm going to replace it with that one there. So therefore, we can say this is equal to k times g prime of x. That completes the proof. That completes the proof. Right, rule number 2 done. Let's move on to rule number 3. Rule number 3 basically says the derivative of the sum is equal to the sum of the derivative. So rule number 3 says, if I may just put it as an expression without stating it, basically says if f of x is equal to m of x plus n of x. This rule of differentiation says, therefore, f prime of x must be equal to m prime of x plus n prime of x. So the derivative of the sum is equal to the sum of derivatives. Basically, that's what it says. Let's prove it. Proof. I'm using 2 functions here, but you can have as many functions as possible. So we are told f of x is equal to m of x plus n of x. Therefore, f of x plus h, this will be equal to m of x plus h plus n of x plus h. Let's substitute in the formula. F prime of x, the formula says this equals limit as h approaches 0 of f of x plus h minus f of x all over h. Substituting these expressions into the formula, we're going to have this will be equal to limit as h approaches 0 of m of x plus h plus n. Remember, this part here is that expression there. N of x plus h minus, open brackets, what do we have here? M of x plus n of x all over h. Right. This will be equal to limit as h approaches 0. Expand the brackets there or remove the brackets. M of x plus h plus n of x plus h. We have minus m of x minus n of x all over h. Rewriting the expression in the numerator, we're going to have this is limit as h approaches 0 of m of x plus h minus m of x plus n of x plus h minus n of x all over h. Using the fact that the limit is a linear operation, this can be written as limit as h approaches 0 of m of x plus h minus m of x all over h, and then we have plus, that plus sign, limit as h approaches 0 of n of x plus h minus n of x all over h. Notice something, this is basically m prime of x plus, and that is also n prime of x, like so. That is the end of the proof. The derivative of the sum is equal to the sum of derivatives. That's rule of differentiation number 3. I'm going to move to number 4, and I'm going to stop on number 4. And of course, your guess is as good as mine. Number 4, it basically says if f of x equals m of x, I would have used g of x here, but it doesn't matter. M of x, if f of x equals m of x minus n of x, like this, your function is the difference. The rule says then, or therefore, f prime of x is actually equal to m prime of x minus n prime of x. Let us prove it very quickly. Proof. So we know that f of x is equal to m of x minus n of x, and therefore f of x plus h will be equal to m of x plus h minus n of x plus h. The formula says f prime of x equals limit as h approaches 0 of f of x plus h minus f of x all over h. Let's substitute the two expressions in there. We are going to have limit as h approaches 0 of m of x plus h minus n of x plus h minus open brackets. This expression must come here. M of x minus n of x all over h. Simplifying the numerator or putting terms together correct accordingly, we have limit as h approaches 0 of, I'm going to remove these brackets now, so m of x plus h minus n of x plus h minus m of x, remember now, plus n of x all over h. This is equal to limit as h approaches 0 of m of x plus h minus m of x. Notice something here now. I'm going to say minus open brackets. Very careful here. N of x plus h minus n of x. Please take note that if you put these two together and open with a bracket like this, that sign here, if you remove these brackets, this term will be negative and that term will be positive like this. All over h. And then I can do the splitting now. This is equal to limit as h approaches 0 of m of x plus h minus m of x all over h minus that minus sign there, limit as h approaches 0 of n of x plus h minus n of x all over h. And yes, you're right, this is m prime of x minus, and that is n prime of x. This is the end of the proof. The derivative of the difference is equal to the difference of derivatives. Rule number 5 will be the power rule. Number 6 is going to be the product rule. Number 7 will be the quotient rule. Number 8 will be the chain rule. And that will complete rules of differentiation. So as far as rules are concerned, and in this video, I'm going to stop here. In the next video, I'm going to just focus on rule number 5, which is the power rule. And that one requires us to apply what we call binomial theorem. So I'll have to start by explaining what binomial theorem says and then move on to applying binomial theorem to proving the power rule. Right, if you're new to this channel, please support us by liking these videos, sharing them, and subscribing, of course, and convincing and inviting friends to subscribe to the channel. We'll be very, very grateful. All right, see you next time.